Hello, good morning, good afternoon, and good evening, wherever you are. My name's Dennis Haggerty. I'm a technical marketing engineer for Cisco Systems, and I work in the Service Provider Access Group. As the name suggests, we're the business unit responsible for access products, those out that are closest to the customer, out on the edge of the network, and we mainly involved with service providers as our customers, so big mobile companies, fixed wireline, that sort of thing. So welcome to the Synchronization and Timing Self-Paced Bootcamp. What we decided we'd like to do is to share with you all an overview, if you like, an introduction to synchronization and timing. What we'll do, we'll cover it in three parts. This being the first part is background material, just explaining synchronization and timing in general terms, some of the concepts behind it, the standards and so forth. Then in part two we'll talk about timing and synchronization in packet-based networks. And lastly we'll go through our portfolio of products and how to configure each one of those for the various scenarios. So looking at the agenda, we have part one is the motivation for synchronization in packet-based and non-packet-based networks. We talk about what it is, why we need it, how we measure it, and as I said at the end we'll go through how we support it in our portfolio. We'll cover in part one the frequency synchronization, an overview of there, about how to measure frequency, about how to distribute it through a network. We'll also look at phase and time synchronization, similarly how we distribute that through a network, and how we measure the quality of it at the end. In part two, we move on to packet-based frequency transmission through packet-based networks, and also phase and time of day through packet-based networks. And so we talk about mainly 1588, IEEE 1588, or PTP as it's known. We talk about the protocol, we talk about reference inputs into master clocks and outputs from slave clocks and so forth. We talk about some profiles that have been defined for PTP and give a general overview of the sort of deployment considerations. And then in part three we talk about the features as they're defined on our product set. So we talk about what's supported, what's not supported, how to configure global options that affect the whole clocking configuration. Then we configure the TDM frequency sync, sync-E. We configure slave clocks, different PTP configuration options. So we go through and show you how to configure each one of those and all the parameters that you can set and what they actually mean. So by the end of part one, you should have a good understanding of general concepts. At the end of part two, you should have a pretty good understanding of PTP. And part three, you should have a fairly good idea how to go about configuring it for SPAG products, and then probably a reference to other Cisco products as well, like the ASR 9000. Some of these slides I shamelessly took from my colleague in Austria, Christian Smutzer, who did quite a number of these slides for Cisco Live events over the last several years. I've taken them and repurposed them, changed quite a few of them to basically go through and give an overview, a sort of timing and sync 101, if you like, an introduction so that people by the end of it can get pretty well bootstrapped into it. So with that, we'll start. This is going to be part one. So part one, motivation. Why do we need it? What is it? So there are two, we could say, or three. I like to think of it as three different things that we synchronize in a synchronization network. And the three of them are frequency synchronization, the second is phase synchronization, and the third is time or time of day synchronization. And depending on the application, they're all important. Some of them are required in some scenarios, some of them aren't required And so by the end of this, you'll be able to understand what should fit where. So the first one to take is frequency synchronization. So if we have a device that requires synchronization of frequency, what that generally means is we take a reference signal in from something, which gives us a nice, square or sine wave, and we then use that frequency source to drive all our circuits for where we're putting data or some sort of signal out on our output. Typically on Cisco routers, this was something like where we defined on TDM circuits before Ethernet. Then we would define clock, source line, and so forth to be able to get synchronization to and from the TDM circuit. We of course do this with SyncE as well today, which is all about frequency synchronization. But the other part is time and phase, and generally people put them together. Phase synchronization is not just about making sure that the frequencies are the same. Your frequency synchronization is making sure that 10 megahertz is 10 megahertz is 10 megahertz. But phase synchronization really is about making sure that two systems understand that things will start and stop at a particular point of time. I will give you some examples a little bit later and then how it relates, and you'll get some good feeling as to why you need it and what the consequences of not having it. And the third is time synchronization, which is there you're really talking about the time of day. It's 1:15 on August the 23rd or something. So typically time synchronization and phase synchronization sort of go together because you define time synchronization at a particular point of time, and that's you can use phase to do that. So time synchronization is probably what most people think of when they say talking about sync. If you're familiar with NTP or simple NTP, which is used to keep the time of day of your PC or something synchronized, then really that's time synchronization. But if you understand that, then that's a good start. But really there's three things we're looking at. We're looking at frequency, making sure that 10 megahertz is 10 megahertz is 10 megahertz. We're looking at phase to make sure that machines do something at the same point of time, and time synchronization is so that we all understand what the day of the week is, and so forth. So who needs synchronization and what sort of applications might it be used for? Well, the first one, of course, and dearest to our business unit and to Cisco in general, is for service providers. Service providers run very large, sophisticated synchronous networks, and because they're synchronous networks, they all need to be synchronized. So every element in their network needs to have a common view of frequency. And the reason for this is quite simple. A good analogy I like to use of this is like you imagine someone at a restaurant is washing dishes, and another person is there drying the dishes. Now, if you have a synchronous network and you're passing dishes from the dishwasher to the dish wiper, then the dishwasher obviously cannot go faster than the dish wiper upper or the dryer, because the dryer will basically overflow with plates. So the rack to hold the plates will become full, and so you'll get an overrun condition. If the dishwasher is slower than the dryer, then the dryer will basically sit there waiting for a plate to get delivered so that they can dry it off. So in general, frequency synchronization is making sure that we avoid situations where we have things like overrun and underrun conditions, where data is sent at a particular rate, and that everything in the network sends it at the same rate, so there's no overflow or underflow, and there's no buffering and so forth in the net. But there's also other applications, industrial solutions. Quite a few factory floors, and for instance, require very precise control of frequency and time. For example, there's a lot of equipment which might need to run at a very specific frequency. A good example is something like newspaper printing, where you can have, imagine, you've seen all on television where the newspaper is on a long roll and it runs through all these printing presses and rollers and before it finally comes out the end as a printed newspaper. Well, you could imagine actually that those rollers have to run very, very close to the same speed and the spin at the same frequency. And the reason is quite simple, is that if one's running a bit faster than the other, then you would tear the paper and the whole print run would shut down. If you run a little bit slow, then what happens is you end up with miles of paper all over the floor. So that's a sort of a simple example, but there are many examples of where machinery needs to be synchronized to make sure that things happen at the same rate. Also, we're seeing use in things like smart grid with electricity grids and power stations and so forth. It's quite important to understand things like phase, because a power system is alternating current, and alternating current has phase. So if you have multiple sources of power, like for instance your solar panel is feeding power into the grid, then it needs to be feeding it in phase with the rest of the grid and so forth. So there's some important concepts there. High frequency trading, probably more of an example of time of day, where you have people need to be able to very accurately timestamp transactions, for instance, to ensure that transactions happen in the order in which they're received, and that they're transacted at the particular point of time that they said they've been transacted. So give you some rough examples of the sort of industries that are interested in this, but that's just a small subsection, a small subset. So going to frequency synchronization in a little bit more detail, the first real reason why we need to synchronize frequency for service providers is to avoid slips on TDM interfaces. Now, by TDM interfaces, I mean time domain multiplex, so standard old pre-Ethernet type transport links. You've probably heard of E1s and T1s. In the US they're called T1. In the rest of the world, the ITU world, are E1. Now these are just interfaces that are synchronous, and the most important part of that is to be sure that the transmit and receive at both ends are running at the same frequency. So if you don't have that, then you're eventually going to get slips on the interface where you either have two pieces of equipment receiving and transmitting at slightly different frequencies. So it's a little bit like your radio is not quite tuned properly to receive the broadcast, and so you'll get problems. Similarly, SONET and SDH optical networks are synchronous networks, and for instance in SONET and SDH contains all these virtual containers, and you need to be able to slot frames into these various containers at certain points in the SONET stream, and so you need the data to be available when it's required, like the guy drying the dishes. So you need to be able to slot the data into the SONET frame. So that requires frequency synchronization. We also see it in radio networks, frequency synchronization, and more importantly, going forward, you can see more phase synchronization required. And similarly, this is going to drive then the requirement to have frequency synchronization pushed out to cell sites. So here on the right hand side we see an SDH container. I was just saying where where you are slotting pieces into SDH frames, and the way that they do this, of course, is by having a clock source which then is propagated to all the devices in the SDH network, and this then ensures that every piece is running at the same frequency and that the data is available to fit in the frame when it should be available. But coming back to the radio networks, this is becoming more of an application now with increased move towards packet-based networks being pushed out to the cell site. Traditionally in 2G they were TDM, but they're moving more and more to packet-based networks. But still we need synchronization out at the radio network. In this case, we're showing where we are having a shooter wire where we're running TDM traffic between our 2G BSC and our 2G BTS. In that case, we would packetize the TDM traffic and run it over a RAN backhaul network. which would take the TDM traffic and put it in IP or Ethernet or MPLS packets and push it out to the cell site. Well, for that to happen, you need to be sure that you have a reference clock frequency running both sides. If not, you'll get traffic overruns or traffic underruns. So just a slight point on these diagrams here, you'll see, let me just try and annotate here for a second. You'll see this symbol. This symbol here is meant to indicate a clock source. So if you like, it's a square wave, and the idea is that you'll see on these diagrams going forward that indicates that someone has a clock source. So here in this sample application for RAN backhaul, we have a clock source connected to the base station controller, and then through a packet-based network you need to push the traffic out to the cell site and the BTS, and the BTS has to be frequency synchronized with the base station controller. So this is probably one of the most frequent use cases that my business unit runs across, and we'll use this this remote cell site as an example going through this this course. So you'll see this come up again, but this is just to give an idea of why it's important, especially for things like service providers, about TDM, synchronous networks, and mobile radio networks. Now, why do we need to synchronize phase? We talked about frequency, now we're talking about phase. Well, there are some radio technologies that require phase. These requirements have been done by the standard setting organizations. The people that set the 3G standards, the 3GPP and 3GPP2. And what they've done is they've defined that they need phase synchronization between base stations. Now, some particular radio technologies require this and others do not. I'll give you a chart a little bit later which requires this. And normally what they say is this requires 3 microseconds between cell sites. So what this means is that each of the cell sites must understand phase and never be more than 3 microseconds out of step with each other. So the way that this works is we have a time reference, and the time reference then through the through the magic of being able to distribute phase synchronization gets pushed through the network, and you take plus or minus, so you synchronize each base station to within 1.5 microseconds of the time reference. So there's a little bit of wiggle room allowed for error and so forth, so you get 1.5 microseconds plus or minus, and that means that that's a maximum of 3 microseconds on any set of between any two base stations. Now, why is this important? Well, it's important for quality of the calls, especially for things like handover. What you'll find is one of the technologies that requires a phase synchronization is LTE TDD. LTE is a 4th generation radio technology, and TDD is time domain duplex or time division duplex method of transmission and receive. So normally the way radios work is you get like a transmit frequency and you get a receive frequency. In TDD you actually get a time slot. So what this means is that during time slot A, the cell site transmits to the handset, and during the next time slot the handset transmits back to the cell site. So it's always like it's a little bit like a conversation that you have with a person. One person talks, then the other person talks back, and so they're using the same frequency if you like, but one is talking, they're taking turns to talk. So the way they do this is allocate time slots. So imagine you're on a cell site and you're talking away and you go to hand over to the next cell site, and your time slot comes available on the next cell site, and you find out you're out of phase. So oops, you're starting to transmit when the cell site thinks it should be transmitting, because that cell site is out of phase with the cell site you've just left. So that means you'd immediately get a drop call. So you'd have to remake the call. So anyone moving between cell sites that are out of phase synchronization in this radio technology would have a drop call. So give an example. I took this slide from Symmetricom. They're good people to, if you're interested in clocking and timing, is to sign up to their webinars and stuff. So they're all free. It's good to catch up on some of the stuff they've got to say, because they have quite a bit of invested in this area. They're specialists in this area. They're now being taken over by Microsemi, so maybe their cell site will change, but their website will change. But anyway, Symmetricom are an interesting source of information for this. This is just to give you an example of some of the requirements in the mobile space for synchronization. So all cell sites basically require synchronization for frequency. Even the old GSM 2G, 2.5, 2.75, 3G or UMTS required frequency synchronization. The LTE, it gets a little bit more complicated. The original LTE, the frequency duplex, which is the standard different transmission and receive frequencies like normal radio, phase is not required. You still need frequency synchronization, but you don't need phase. Then when you start to get to TDD, this time duplexing, where you have transmit receive from the handset, does it with time slots, then you'll find that you'll need phase, and that's to get around the problem with handovers, which I explained before. I believe some of the Chinese standards already use TDD or require phase in some of their different implementations of various CDMA standards. So some Chinese technologies might already be requiring phase. But there is some parts of LTE, traditionally, even if they're not using TDD in quite a few markets, that will require phase synchronization. The sorts of technologies we're talking about are things like MBMS. They've got broadcast, multicast services on LTE, which are going to require phase synchronization. Also LTE Advanced, which includes a lot of sub-technologies. So there's things like the LTE intercell interference technology, and this is where you have what's if you want to Google HETnets or heterogeneous networks, it's the ability to put small cells inside macro cells and not have them interfere with each other. And there's some very smart technology in the LTE Advanced area. But so there are a broad range of technologies there, but just about all of them require some form of phase synchronization. And to give an example of why we need to synchronize time, here we're talking about time of day now. So the one example is I've given already of high speed, high frequency trading, or doing things like keeping log files consistent. If you have a very large network and you're running something like an electricity grid, and you have a lot of devices out there that are measuring parts of the network, then you need to be able to correlate what's happening across your network. Then you need very good and very consistent time of day to make sure that you can then figure out in what order things are happening. One example of this too is for things like performance management. With Y1731 as a technique for measuring the performance between two pieces of customer equipment. So here we would have a customer who's got a site A, and then he has another piece of equipment in site B, and there's a service provider who's providing some form of service between the 2 points A and B. But the customer has some very strong requirements for delay or bandwidth, so they can put Y1731 on their equipment and have it running to be able to measure the delay. And the 1731 sends out a delay message. It uses timestamps to be able to find out what the when the packet was sent, and then this at the other end you get a reception timestamp which says when the packet is received. Now there are two ways of doing this. There's a one-way and there's a two-way delay. So obviously for a one-way delay, if the site A timestamps the timestamps the packet when it leaves that site, and it timestamps the reception when it arrives at that site. If time A and time B, if their clocks aren't synchronized, then of course that's a meaningless result, because you have to be able to ensure that that both of them are running the same clocks, or the measurement is worthless. There is a two-way method whereby you send it out and then you wait for a reply back, and then it's much easier to do a two-way delay because you calculate it at this end here. And what that means is you can use the transmit and receive, and you can figure out if the clocks are out of sync. It doesn't really matter. But if you're doing things like one-way delay, this is an example of a case where you would want to have very good time of day synchronization in your clocks. So that's just to give a background of like why we do this, who's interested in doing it, and some of the consequences and ramifications of not doing it correctly or not having a properly synchronized network. So what we'll do now is we'll go on to basically give a more detailed view of frequency synchronization. So I know it might seem a bit confusing at the moment, but if you just bear with us for a while, we'll make it quite clear what's actually being synchronized with frequency, what's been done with phase, and what's been done with time. So we're going to focus mostly in the next, probably the next 45 minutes on frequency synchronization. So frequency synchronization, there are two ways to do frequency synchronization. There's a physical distribution and there's a packet distribution. So we'll talk about the physical layer first, and then we'll talk about the packet a little bit more later. And in part two, we'll go right into packet-based frequency distribution. But at its simplest, you've probably been aware of frequency sources, because most Cisco equipment and most network equipment has some form of synchronization input. Typically, you've probably heard of bits. And what bits is it's a technology for giving signals for frequency sources to network equipment inside, data centers and service provider premises. I use the expression bits here. I should point out that it's actually an ANSI term. It's a US ANSI term. There is an equivalent term of SSU in the ITU world, a synchronization supply unit, but basically you'll hear me talk about bits, and when I mention bits, I'm talking about an external physical frequency source. It can be either 2 megahertz in the ITU world, or it can be 1.544 in the NC world. So here we see a router switch module, and in it you'll have a sync input port, and these sync ports will be bits based, and they will be you'll see that they'll have a cable plugged into them. It looks like an Ethernet port, but actually it uses different pinouts, 1, 2, 4, and 5, and that will have some sort of frequency source. The sort of frequency sources we normally talk about is there can be like a 2 kilohertz signal that can be come in. You can also have synchronous Ethernet can be a frequency source. You have a bits port like I've showed there. You can see at the bottom here we have a line interface on a card. So this is like you have a GigE or a 10 GigE interface, and you can actually get the frequency from synchronous Ethernet in one of these ports as well. So any sort of TDM to take a frequency source, or a bits port, a specialist port to take frequency source, or gigabit Ethernet, 10 gigabit Ethernet as well to take a synchronous Ethernet. You can take, you can get frequency coming in from just an ordinary E1 or a T1 link, and this is where I referred to earlier. If you configured routers in the pre-Ethernet era, then it was you would always configure a clock source line, which meant you were taking your clocking from the TDM circuit that you were connected to. There is also specialist frequency inputs. One of the most common these days is a 10 megahertz signal, and typically that's taken from a GPS receiver. And so the GPS receiver will have a port on the front of it, and you can plug that into, then be a plug on the front of your router, which will be a 10 megahertz port. Now, typically you can define one or a number of these inputs as your frequency source, it's just a matter of configuration, which we'll cover in part 3. The other way of doing frequency distribution is by a packet-based network, and I said we'll talk a lot more about that in the next part. They're both two approaches to solve the same problem of sending a frequency reference, like a source of frequency, out across into a network element, and then that network element is then synchronized with the rest of the network, and it can also then send that frequency source out through its interfaces as well to downstream devices. So I didn't really cover, but what is frequency synchronization and having a source of frequency doing for you? Well, really it's quite simple. All it's trying to do is to say that if you have 10 megahertz, you're at 10 megahertz, you're not at 9.9, you're not at 9.99, you're not at 10.01. That your oscillator that is driving your data circuits is running at 10 megahertz, or whatever it's required to be, 2 megahertz if it's an E1, or 1.544 if it's a T1. And all it's saying is, it's 1.544, it's not 1.55, it's not 1.53, it's actually 1.544. So what it's doing is just ensuring that you're as close to your required nominal frequency as you can be. And there are various ways to do it, but all that they have in common is that you have a frequency source from one of these inputs, and then your oscillator can then run tuned to that frequency. From the point of view of frequency synchronization, I've given you an example of a router there at the top right, which is one of our ASR 903 RSP modules. You can see there that it has a bits interface. It also has a 10 megahertz input. Either of those can be used as a frequency input. So if you have those connected and you have it configured to take them in as a frequency source, then you are technically what's called synchronized. So we use the term synchronization, but technically synchronization is when you are running as frequency aligned. Synchronization is when you're also aligned with phase. So in the case here, just pointing out that even though you have two devices here, we're showing this picture here, we have two devices, and we're just showing their frequency, like an output of their frequency if you'd have it on an oscilloscope. And you can see that they're actually frequency aligned, because they're the number of ups and downs, peaks and troughs is the same on both, and that one's not catching or lagging behind the other. But you'll see that they're actually out of phase, and the reason is that when the circuit starts to change from positive to negative, or when it reaches a peak, the other one is a little bit behind it. So in this case, the signal from system A relative to signal of system B has a phase offset, which is normally mentioned as theta. So what you can say then is that if they're frequency synchronized like that, two of those devices, even though they're out of phase, if you take some signal out of those devices like we have shown above there, then you're getting the same value. So both of those signals will be 1.544 megahertz. One won't be 1.53 and one won't be 1.54. They'll both be 1.544. So that's when you say that they're frequency synchronized. As I showed, the difference in the position of the rising edges is the phase offset. And it bears saying as well that if you have two frequencies that are constant phase offset, so the offset never changes, theta never changes, no matter when you look at it, then they're phase locked, and they have to be frequency synchronized. So it's sort of like driving a car. You know, if you are driving a car down a road and you're always 100 meters behind the car in front, then you're going the same speed. And it's sort of the same principle. If you always have the same phase offset between two signals, then you are frequency synchronized. You're running at the same frequency. So first I wanted to run through just some fairly basic definitions when we're talking about synchronization, particularly of network elements. You'll hear these expressions going forward, so I thought we should just go back and define them to make sure that we understand them. So here what I'm showing, just to explain the diagram, I'm showing here that we have a system clock on our device here, which is in orange, and we have defined two clock sources. So we have our machine plugged into two sources of time, and we have defined that we want clock source A, and then if we don't have clock source A, we're going to have clock source B as a backup. So in a normal state, we're locked to input A, so that means A is a valid reference source, and we're synchronized to it. So that's what's called locked, and that's the state you'd like to see. That's the one you really want to be in there under normal situation. But what happens if you only have one source and you have no second source, or the second source has disappeared, or you only have one configured? Then what happens is when you run out of, when you lose connectivity or you lose your input A, you go into what's called holdover mode. So holdover mode is when you were synchronized with something and now you're not. And this is important because holdover performance is a fairly important characteristics of a network element, and particularly of the oscillator within a network element. And in this case, the holdover, it can be of very good quality, because if you have been synchronized with an input for quite a period of time, your internal oscillator, if you like, is tuned to the frequency reference that you're using. And if it's been tuned that way for quite some time, and you don't get wild temperature swings or something like that, then the holdover performance can be quite good for quite a period of time. Depends on the quality of the oscillator and the cost and a few things, which we'll explain in a minute. But so this explains one sort of misunderstood thing about clocking networks. It's actually not vitally important that you have a reference source at all times. Of course, it's a good thing to do, and that's what you'd want, and that's what you'd aim to achieve. But what I'm saying is, if you go into holdover for a few minutes, hours, a period of time, it's not a disaster, depending on how good the quality of your oscillator and how good the quality of your clocks are. You can actually go along in holdover mode before things start to go wrong. So holdover is a condition where you were synchronized and you're now not. And this is really what you want to avoid, is where you're free running, and in a free running system you have no sources, so you have no signal to synchronize to, so you have no frequency source. So as I showed in the diagram with all the different frequency inputs, this is when none of those frequency inputs are working properly, and you do not have any frequency source. Now, free running normally means that you've never been synchronized, so you turn the box on, there's no configured clock source, or the clock sources aren't available, so the machine will be in free running state. The other time it can be in free running state is if you've been in holdover for too long. Many devices, after a period of time like 24 hours, will decide that they've been in holdover for too long, and they will go into free running state, in which case they'll basically forget about the tuning information they had from their frequency source, and they'll just go back to running at their ordinary old frequency, whatever that is, good or bad. Free running is not really what you want. The other thing to talk about is revertive mode, and now these will become important in part 3 when we go to configure these, because you'll configure whether you want revertive mode or not. And revertive mode is where you have multiple clock sources. In this case, we've configured clock source A to be our primary, clock source B is to be our secondary, and so we have clock source A, and then at this point here we lose clock source A for various reasons. Various things can happen which means you lose it. So we go back to clock source B, and clock source B then becomes our reference frequency for our system clock. And what revertive mode means is that at the point your primary clock comes back, you'll revert back to using your primary source. And normally this is what we configure. Otherwise it would stay using B until something happened, and then it would only go back to A if it had to go through and find another clock source. So there's the basic principles that we want to cover, free running, revertive mode, holdover mode, and locked. And of course locked is what we want. Now what I want to just talk about and touch was the frequency accuracy. Now, of course, we being a very technical world, it's one thing to have a quality clock and to have a frequency source and to be using that frequency source, but now we need to measure just how accurate that source is. And there are some various metrics. The most basic one for frequency accuracy is where we calculate the frequency accuracy, which tells how much we move out of phase with the reference signal over time. So normally it's averaged over a long period of time. So instantly there's sort of other measures, but so what this says is if you have a reference signal A and you have a machine that's giving you a signal B, it's like how much does signal B move relative to signal A over time. So the way that this is done is you take an observation period. I said 1 second here, but it'd typically be longer than that. And then at the end of 1 second, you can see each one of these, there's a slight gap opening up here, and then it jumps a little bit. And then at the end of 1 second, you've defined that there's a 1 nanosecond phase offset between your reference signal and the signal that you're measuring. Now, we're talking about frequency accuracy here, but I mean it's the phase that's shifting. So so you know that the frequency has changed a little bit because you've got one's running a little bit slower than the other. So what you do is you calculate how many the phase offset is after your observation, and so you can say we're 1 nanosecond we've changed time over 1 second of observation, and so that gives us 1 in 10 to the minus 9, or 1 part per trillion of frequency accuracy. Some other examples, you might see 50 parts per million, 10 parts per billion, and that would be sort of fairly, you'll see it written, and you'll see as we go through this presentation, you'll see that we start to talk about parts per million and parts per billion as well. So that's our main metric for frequency accuracy. So we've talked so far about being able to take a frequency source into our network element, so we plug it directly into our network element, and we then use that to drive our our data circuits using that frequency source. However, it might be quite likely that not every device has a frequency source attached to it. So, and even if they do, how do frequency sources, how do they spread their information around the network? So there are 2 ways that basically you can distribute clocking within the network. As we say, we can do frequency distribution over physical layer, and we can do frequency distribution over packet layer. And so we're going to look at that in a little bit more detail. So we'll spend a couple of minutes on this slide. So here we have our sources. We have our source signal. So we have some sort of bits source or some sort of primary clock that is able to give us a frequency source, and we plug it into a network element sitting here. Now, don't worry too much about the terms above these devices, but basically when you see a SEC or an EEC, that's the clock quality that you would associate with a normal router. SEC is a sonnet term, and EEC is a sync-E term, and we'll show you a chart of those in a minute. But don't get too hung up on the actual the acronyms. But we're just saying these are ordinary routers. So in this case, we are taking a frequency source in. It could be from a bits input, an SSU, and then we can send that frequency through the network. And as we said before, when you would configure this normally in the TDM world, then you would configure a clock source line on this interface, and you would use this as a frequency source on this network element. You would use the reference frequency here, and so what would happen is this frequency would then drive the circuit out towards the next SEC. It would have clock source line, and then it would have clock source internal here, and it would drive the frequency until it gets to an Ethernet based router. And then the traffic, if it's IP traffic, we might put it over an Ethernet network, and then we can use sync-E to do the same thing. So we can configure this device here to take its frequency reference from this line, from this TDM circuit, from the sonnet circuit, and it can then use it to drive a sync-E circuit out to, I put a mythical cell site here, but basically you can then use that frequency source to drive the clocking that's required on the cell site or whatever else your application is. So that's how you would drive it through a physical frequency network. Now I've mixed sonnet and SDH here, but it could be all sonnet, could be all T1s, TDM, E1s, it could be all sync-E. It doesn't really matter, because the principle is very much the same. It's using a physical layer to distribute frequency. What you could also do is, if you had another building, if you had another source of frequency, then you could actually, if you had it available, then you might be able to plug it into this router here and define to take it there too. But if you don't have it available, then you can send it over the actual data networks. So I should just explain too, there's an in-band and an out-of-band thing happening here. So in this case, we're normally sending data over these circuits. So this clocking is all in-band, and so you're using the data circuits to drive your frequency information to distribute your frequency. But you could have an out-of-band system, which I've shown here. If you had a clock source on each one of these devices, then that somehow there would be an out-of-band frequency distribution network who would be somehow connecting these together. So the whole three of them there'd be like another network of frequency sources, if you like. So that's how it's done with physical layer. With a packet layer, then a different approach, but you end up with the same result. Is you have a frequency source into a packet master, and typically we're using 1588, and 1588 uses the term of a master and a slave. So these are standard terms, and the master uses this clocking information and uses it to generate a packet stream. And the packet stream contains timing information, which the magic will explain later. And then at the end, where you require the clocking, you'll have a slave, and the slave will use that timing information to generate a clock source, and then that clock information can be used to drive a frequency out to, for instance, if you need it at a cell site or some piece of equipment that needs frequency. So the thing to get away here is that there are two different approaches to solving the same problem, where one's based on the physical layer and one's based on a packet. I will also point out that the physical will give you a better result, just because of the nature of physical networks. you get a better result if you can use frequency distribution using a physical layer like SyncE. You'll get a better result than if you use packet. Now, of course, you don't have SyncE everywhere, then you have to use packet. But just in general, the result will be better with a physical interface. Now, another concept to touch on is clock recovery. You sort of saw that at the end of those in the previous slide, where you saw that the cell site was getting clock coming from a distributed network. So the frequency had been distributed through a network, and at the end there was someone able to take advantage of the clock. Well, in fact, all the network elements are doing a similar process. And so every network element will do this thing. It's called clock recovery. So when you are a network element and you have an input signal, so you have some sort of frequency input, it's either a dedicated input like we showed with the bits interface, or it's a data circuit that you're actually using like SyncE or Sonnet or something. You will get the frequency coming in on that data circuit which you've defined to take your source from. Now, that, depending on where it's come from and how it's where it's been, that signal can be good, or it can be a little bit can be a little bit dirty. It can have a bit of jitter in it. So there's a process called clock recovery, and what clock recovery does is some electronics on the device that take that input circuit and filter it and work in conjunction with some pieces of electronics to tune, if you like, in one of a non-technical term, to tune the local oscillator, and the local oscillator will then be a reflection of the input frequency which it's got. But the signal might be cleaned up a little bit, just taken a bit of the jitter out of it and so forth. So this gives you the this then gives you your local oscillator is synchronized then with the input frequency, and then that local clock is used to drive all your data circuits to all your downstream nodes. So in the previous slide, that's what's happening. I'll just go back. That's what's happening in each of these devices. Is they're taking clock from an input data circuit, and then they're undoing clock recovery, and then they're using the recovered clock to drive the frequency of all their data circuits that they have then configured on them. So, like the physical distribution method, the packet distribution method has the same job to do as we've seen before for a PTP or a packet-based distribution method. There are two methods that I sort of talk about a little later on. One is called adaptive clock recovery, and the other one is the PTP, and we'll talk mostly about PTP because adaptive clock recovery is quite limited in most cases. So in this case we have a reference clock into a packet master. A packet master then, if you like, does its own clock recovery from the reference clock, and the packet master will then generate a stream of packets containing timing information, which will then go to the packet slave. And the packet slave will receive that information and will then do recovered clock. So what it will do is it will use the stream of packets that have been sent to it over the network, and it will use that to recover a frequency information from it. So, and what it's trying to do is it's trying to synchronize its frequency with the frequency of the oscillator on this device here. So it's, by the end of this process of this clock recovery, what you want is the packet slave running at the same frequency of what the packet master is. That's really what you're trying to do. And then of course, once you have your oscillator running at the same frequency as the other guy, then you can use that oscillator to to drive circuits like SyncE, to TDM circuits and Sonnet circuits and so forth, so that you can then use that clocking information to drive your downstream circuits or pieces of equipment that need clock. So the three basic steps there before, like the generation of the packet stream, there's a transfer of the packet stream over the network, but similarly we have this process of clock recovery where we recover the stream of data and we turn it into a physical frequency, and we use that to condition the local oscillator. We talked a little bit about noise and jitter and wander, and so I thought I would just put a slide in to explain what is jitter and what is wander. So at its basic, noise is because the real world is not perfect. We have in frequency with a physical medium, we have problems in the real world with electronics. We have problems of induction on cables. We have reflection whenever there's a bend in the cable. Whenever there's a terminator or a join, you get reflections of signals. You get interference from things like power circuits and so forth, or other crosstalk from other pieces of cable in the same conduit or so forth. Really, it's just a reflection of the physical world and the issues with electronics not being perfect. So the way a timing signal works is at some point you define these things called significant instants, which I won't really get into, but at some point you define where the signal starts, whether it's a particular voltage or signal strength or so forth, where you define. And what can happen, of course, is this can move. This curve can flatten out a little bit. You can get reflections, which mean the signals arrive a little bit early or a little bit late in charge of it. You can the signal can get distorted through inductance and so forth. So the details aren't that important, but the idea is that just the signal can just get a bit dirty. It's like if you photocopy a document and then you photocopy the photocopy and you do that 5 or 6 times, then you're sort of getting the idea that these signals get a little bit degraded, especially as they get further and further away from the primary reference source. And if you want to then take that and put it on an oscilloscope, you'll start to see things like this histogram below, which is a reflection of the error. Here, this is a time interval error. So what you're actually seeing is the piece of equipment that's receiving the signal is trying to figure out exactly when this pulse starts and ends, and you can see that it's actually not all around zero. It's actually a bit of a bell curve because there's a little bit of jitter in the signal. Jitter being a short-term, if you like, a shaking of the signal. So here you can see that the signal has moved a few picoseconds off in either direction based on the which particular cycle that's received on the oscilloscope. Well, for packet-based networks, we have similar problems, not exactly the same cause, but we do get noise and jitter on packet-based networks. Normally in a packet-based network, you send out a stream of timing-related packets. It's sent at varying rates. Typical rate is 64 packets a second, but it can vary from like 1 or even 1 every 8 seconds through to 128 per second. But let's say 64 is a typical rate. And so you're sending a stream of packets out, and there's some clever hardware that's used to do things like timestamps in the packets, which is used to transmit the timing information, and we'll go to the details of that in part 2. But of course, what happens is there are packets that are sent, but some packets are delayed. There might be some corrupted, although that's not an unusual problem. Just throw them away. But the main thing that will happen is that the packets will get a variation in their delay. So you might send them 64 a second, but instead of arriving every 64th of a second, some might arrive after a 60th of a second, and some might arrive a 70th of a second apart. So rather than being absolutely regular 1 every 64 a second, they may you may get a few more in 1 second than in the other. So what this does is the timestamps in this case are used as like the information that's required to recover the timing information. So it's labeled here as significant instances as well. But basically all that's saying is that the important information is these timestamps, and when and how they arrive can vary based on packet delay. And that, of course, is a source of noise. Noise here not just meaning sound, but noise meaning degrading your signal, which means you lose timing information, or inaccuracies in your timing information come in as a result of this. And just digging into noise for packet-based timing, packet delay variation. So if you dig into this a little bit more and give you an example, packets, of course, go through routers, which are store and forward platforms. They're different to the synchronous data networks. That's why they all have to be frequency synchronized, is because every slot is basically filled. But these are stored and forward devices, and so as you get a typical day in the life of a packet comes in, there's you've got policing, there's queuing, then there's all sorts of ingress, classification, quality of service issues. Then you go through forwarding decisions, and then you go through the whole egress, queuing, quality of service, scheduling, shaping thing as well. So what we're showing here is two packets that are coming on a timing source. We have a packet which is red, and we have a packet which is blue. And packet delay variation simply means that the propagation time of this packet through this device and end to end is not the same for red as it is for blue. And normally packet-based timing systems do not like this. This causes them some trouble. It doesn't matter what the latency is. Well, within limits, the latency, it's good if it's small, but it's the change in latency. So if one packet takes 10 microseconds and the next packet takes 80, then that's a problem. Generally, if one takes 15 or 60 and the next one takes 61 and the next one takes 59, that's good. But you don't want a big variation in the propagation time. The other thing that they don't like is where you have here this packet purple, because these packet-based networks are typically two-way networks. So there's timing information going in both directions. And it's important that there's no asymmetry. And what this means is that the propagation time of a packet going west, say the blue or the red packet, is not the same as the propagation time for the traffic going east. So that's actually not very good for a lot of packet-based and two-way timing systems as well. And there are various reasons for that, which I'll explain when we get to 1588. Now, just showing you in a little bit more detail just what this does to our packet-based timing stream is when we have a device that has just give a typical scenario of how packets pass through a device and what sort of what the impact that is on the packet delay variation. So here we see a graph where one's on the left has been blown up onto the right to give an example in a bit more detail. But you can see here on the left, here on the x-axis we have like the number of packets that have been observed. So we're watching a number of packets and we're plotting the packet delay variation. So you see from up the y-axis is the packet delay from the minimum. So what we've done is we've taken all these packets, say here we're at 5,000 packets, and the minimum time for a packet to go through this device has been then put at 0. So we say 0 is the baseline. Now whatever that took, whether it was 5 milliseconds or 5 microseconds, and then anything above that took longer than the minimum, that's what's been charted here. So we're leaving the device here and it's sitting in an idle mode, so all the packets are basically transiting the device at the same sort of the same latency. So there's no variance really from the minimum, maybe a few nanoseconds here and there. Then what we do is we put some background traffic on. So this is the background traffic that's been added, and we don't have a strict priority queue. So we have no quality of service, no strict priority queue. And then we ramp up this background traffic. So we basically load it up to 80%. You can see all of a sudden that quite a few packets still arrive in the minimum period of time, but there's quite a few that arrive 14 microseconds later. So this is a very large variation really in your packet delay. So this is the sort of thing that you really have to watch out for. And then what happens is you can then switch on strict priority. For instance, you start putting some quality of service on. In this case, it didn't seem to make much difference. You reduce the amount of traffic down to 20%, and you can see that it improves markedly. A lot of packets now are starting to be delivered down towards not much beyond the the original lowest packet time, the minimum delay. But you can see that a lot of packets are being delayed 10, 12, 14 microseconds. So the thing to take away from this is each piece of equipment will have its own signature like this. It'll have its own features as to how it behaves, and it'll be based on not just the architecture of the device. It'll be based on how it's configured. If you use quality of service, if you have strict priority queues, hardware-based switching. There's a whole bunch of reasons why this will have different characteristics for each particular device. And there's also an asymmetry one here too. Some devices do have asymmetry. Traffic goes at a different speed through the device in one direction than it does from the other. The point to put all this out is basically this. It's important for packet-based networks, of course, is the quality of the underlying network that you use to take the packet stream is very important, and the devices in the chain that are switching these packets is also very important, and how they're configured and how they behave. So very important for all this is to basically, whenever this has been proposed for a customer environment or you want to deploy it in a network, that you test it and understand what the devices are actually doing. Just covering packet-based for clock recovery. I sort of touched on this a little bit previously, but as we said before, there's a clock recovery process where a device needs to recover the clock and condition its local oscillator to be in tune with the incoming frequency reference. In a packet base, you don't have that frequency reference. You're relying on these packets arriving and trying to figure it out. And so basically the way it works is you have a process whereby you select the packets. And this is pretty simple. You basically listen to the incoming packet stream for a while, and this takes some minutes, and you figure out which are the quickest ones to arrive. So the ones with the lowest latency, the lowest delay, and you figure they're the ones that you want. So in the previous chart, they would be all these packets down here on the bottom row. So these are the packets you're going to want, the ones that are going through the network with the minimum amount of delay. So you take those packets and you throw the rest away. You use your local oscillator, and then there's a piece of very clever software called a servo. And what it basically does is figure out from the timing information it's getting from the remote master, and using the timestamps that are coming in the packets. It feeds this information through a piece of electronics called a PLL, and what it then does is it comes out with a reference signal, and that reference signal then can be used to drive the internal oscillator, and then you've got a recovered clock. And so your packet slave would then have a frequency available here, a recovered clock that would be synchronized with the packet master here. So important factors here, of course, that we've already covered: the packet delay variation and quality of service in the devices in the packet-based network between the master and the slave. But of course, the quality of the servo is pretty important. The PLL and how many you've got and what quality they are, and also the quality of your local reference oscillator is also quite an important consideration as well. And again, a lot of those just come down to cost-based trade-offs when the engineering of the device has been done. Okay, so moving away from clock recovery, another important concept we need to cover off is the issue of quality levels and quality traceability. So we'll spend a little bit of time on this slide. Really the problem that we're trying to solve here is, a network element needs to know that it's connected to a valid clock signal. And it needs to know the quality of that signal, like if it's a good clock or if it's a bad clock. And so there needs to be a mechanism whereby we can determine at any particular network element, what is the best signal to listen to for clock, and what is the quality of what I'm listening to. And so the way that this is done is using various mechanisms to do quality level. So let's take an example from here, from the left-hand side. We have two network elements. And again, don't worry about the acronyms too much in a minute. We'll cover these in a little bit later. And we have a primary reference clock. Okay, primary reference clock is the guy you want. He's the it's the highest quality clock that we would have in the ITU world. And we have an SSUA, which is a lower quality clock than the primary reference clock. Still pretty good, but not quite as good as a primary reference clock. And I'll give you some numbers in a minute. So one network element is connected as its reference source. It has the primary reference clock, and the other guy has the SSU. Now that network element, of course, is recover the clock and used to drive the frequency of this circuit. And so you see here there's a clock information being passed down this circuit, sort of indicated by the dots. So this network element here has two circuits connected to it. It has this one here connected to the north network element, and this one connected to the south network element. And so what you could do is you could define on this network element, you could say, well, take your clock from this guy, okay? And that would be valid. If you took the clock from that guy, you're using the best quality clock available. But the problem is then, what if that reference clock is not available? Well, you need to use the second one. Or what if this guy doesn't have this link here anymore? How do you know that the northern network element is still connected to the primary reference clock? So the way this is done is this mechanism of transmitting quality levels. And each of the mechanisms we've talked about so far, whether physical-based methods or packet-based methods, approaches this problem slightly differently, but they all do the same basic task. And what this allows this network element to do is to figure out which it should use for its clocking reference, and then when it gets it, when it recovers clock from the source that it has decided is the best, it then uses that information and sends it down to network elements further downstream. So this is kept, across all these distribution networks. They have a similar mechanism for this. Each of them slightly different. We'll go through them in a minute, but it's to solve the same problem. And so when you configure this network element, you can configure it two ways, and we'll touch upon the concept now, but we'll do a little bit more of it in part 3. But there's what's called QL enable mode, and there's QL disabled mode. And what QL disabled mode means is you don't listen to the quality levels. So you would just define, sorry, my northern router is number A, is my primary reference I want, and my backup reference is the southern router. Okay, so you just put a priority on it. Now, as long as network element north is available, it's going to use it. It doesn't matter if network element north is connected to this primary reference clock or whether this link here is broken. It doesn't matter, because it's ignoring the quality levels. It just says, while I can still talk to north, I'm going to use north. So QL disable mode is very static, doesn't take account of failures in the network, doesn't take account of changing conditions and so forth. QL enable mode, what that does is it uses quality level in the determination of which clock to pick. So although there is you still can define quality level. You can still define, I want this to be my priority 1 clock source. You can say, well, I want this one to be quality 2, and it will stay like that. But if this all of a sudden becomes not a primary reference clock, it will switch over to 2, even though this is still available. So network element north can be still available. This link is still up. We're still getting a frequency coming in that link, but this network element will say, no, I'm sorry, I've seen the quality level coming down this line, and the quality level is no longer primary reference clock, so I'm going to switch over to this guy because SSUA is the best quality level that I can see. Okay, so what this means, just underneath those lines there are just saying, well, what is the order of which it uses to determine which is the reference clock. So this is just, if you like, this is the decision tree. In QL disable mode, you have external commands, like you can just say use A, use the north. Then 2, like if the signal's not failed, use it. And then number 3, if it has 2 clocks and they're both working, then it'll pick whichever one you define as the higher priority. In QL enable mode, again, you can override it and say just use A, no questions asked. But then it'll say what's the highest quality level, and if they're the same quality level, then it'll say have we got a signal failure. But if they're both signals are up, then it will go on the local priority. So it's just this is the sort of order in which the decision is made as to which clock source to use. Okay, so we come back to a slide that we sort of touched on before, where we saw a physical layer distribution, frequency distribution, and we saw a packet-based frequency distribution. And as before, we had a frequency source coming into our, again, we saw this is an SEC, which is just a normal router from a clock point of view, and this is a normal SYNC based router from a clock point of view. And what we've done here is I've just overlaid the technology that's used to pass on clock quality. And in TDM, it's what's called SSM. There are a series of bits that are carried in the in the overhead frame, in the overhead fields in the frame for things like T1 and E1. And SSM, these bits will actually define the quality of the clock that the signal represents. So that's how that problem is solved for TDM Sonnet type networks. For Sync-E, it uses a different approach. It's called ESMC, and ESMC is a synchronous messaging channel, and what that is a few data packets are sent over the same link to indicate the quality of the clock that has been sent over that Ethernet link. And in a packet-based network, we have the concept in PTP of clock class. And clock class is a series of values, again similar to ESMC and SSM, which indicates the quality of the master clock source. So in this case, a master is configured to have a reference from some form of master. It is configured to give a certain clock quality. If it no longer has a reference, then it will lower its clock class to indicate that it no longer has a good quality clock, even though the packets might continue to pass from the master to the slave. So they're sort of important terms to know. SSM is for TDM, traceability of clock quality. ESMC is for Sync-E, and PTP clock class is for 1588. And so to give you an example of how this works, I've taken the example of synchronous Ethernet, and just to show you how this this process works in in fact. Now, ESMC, there's a couple of things I should just explain about ESMC. People somehow think that when, it's a common thing I hear is that Sync E consists of packets. Okay, that's not true. Synchronous Ethernet doesn't consist of packets. What Synchronous Ethernet does is it's actually a feature of the PHY and the router at the other end. It actually doesn't change anything on the circuit. All it means with Synchronous Ethernet is that it has the ability, like a TDM router, to take clock in from a line on one Ethernet circuit and use it to drive its transmission of all its Ethernet circuits. Normally what used to happen was every Ethernet circuit would just negotiate a master slave between each end, like a transmit and receive slave, and it would then just use the frequency of the master on the slave. So every circuit could be running, plus or minus the frequency. What SyncE did was change the router so that the frequency that's used as a source is then used as a frequency source for all transmission from that box. So we'll cover this a little bit more later, but in general, just get the idea that it's actually not a feature of Synchronous Ethernet. There are no packets in Synchronous Ethernet. The packets that are in Synchronous Ethernet are ESMC packets. And ESMC packets are only used to carry the clock quality information. So it's not actually used to carry the timing information either. So ESMC, it runs in a OSSP protocol, Organization Specific Slope Protocol, which is defined in 802.3, and so it's just a few bits of data that are passed around about clock quality. So just something to remember. Synchronous Ethernet, really there's no packets involved. ESMC, yes, there are packets involved. And the way that it works is, in this case we have a primary reference clock here, which is the the highest quality reference clock that we can have, and we have a Synchronous Ethernet circuit connected to an SSU, which is the next quality level down, and that has an Ethernet circuit which is connected to your ordinary router, which normally is an Ethernet equipment clock. It's an EEC, that's a normal router here down the bottom. And what happens is the primary reference clock, when it comes up, it says, well, I'm a primary reference clock, so it becomes the clock master, if you like, the clock source internal of this circuit, and this guy then takes the frequency from that link, and it says, oh, this guy's PRC, I'm going to listen to that because obviously it's a primary reference clock. I'll take my synchronization sources from there. So what it does is, in the opposite direction, it sends what's called a do not use. Now this is really to stop timing loops. What this means is you don't take clock source where you've just sent it, otherwise you would be like you get an infinite loop like. So wherever you take your source from, you send a do not use back, because you don't want this guy to then take its input from where you've just sent it. Again, to stop loops. Now this signal is this SSU here, it sends, we're down this circuit, it becomes the master of this circuit, and it says, oh, this circuit's connected to a PRC, my clock is synchronized with a PRC. And the EEC says, thank you very much, I'm going to listen to you, I'm going to use you as my input, and drive its internal oscillators for all its other circuits. So what it's going to do is, all its other Ethernet circuits, it's going to use this the clock that is recovered from this Ethernet port here, connected to the SSU. Similarly, it sends a do not use back to the SSU. Now this process repeats further down the chain. This EEC then says, oh, I'm the master of this circuit. It sends a PRC down to this guy. Similarly, this guy is sending a PRC to this SSU. Again, the PRC is better than the SSU. It sends back a do not use, and so forth till we get to the end. And then we want to look at what happens if we get a failure somewhere in the network. In this case, we on the left hand side, nothing much has changed. We have a primary reference clock feeding down to the EEC, but this circuit here is broke. So this guy was getting his input from this circuit. So what we now have a problem where we need to go through a form of reconfiguration. So the EEC said, well, he sends a message to the SSU saying, I'm an EEC. And the SSU says, well, I'm an SSU. So obviously SSU A wins over EEC because it's a higher priority, high quality clock. So this guy then starts to say, well, I don't have a PRC reference anymore. I've only got an SSU reference. So it sends a SSU reference. And then when everything settles down, you get what you'd expect here. This guy says, okay, I'm now taking my clock from SSU A. I'm sending a do not use back. And because this is now my input frequency source, I'm now becoming the master of this link, and this guy is going to receive synchronization down that link and be told that it's connected to an SSU A device. And so, as we said, the reason behind all this, you can see how it works, is to present timing loops. And you can imagine this in a ring. You could get timing loops, and also stale clock information, like where you've been told you're connected to a PRC and someone forgot to change the batteries, or disconnected the device a week ago and the network is unsynchronized. So in this case, of course, depends how good this SSU is. If this SSU is in holdover, because it's not connected to this primary reference clock, so this SSU here is in holdover, say it doesn't have a source. But obviously the holdover from an SSU A is going to be a lot better than having this device being in holdover itself, because the oscillator on an SSU A is better than on an ordinary equipment clock router. So just explaining, some of the standards. Very important, actually, that to get across that standards are a very important part of synchronization and timing. You've probably detected that already. A lot of the references for these slides have come from standards documents. And here are some of the standards down the left-hand side, and they've defined the levels of clock quality. And here you see them. There's at the top, there's what we call a PRC or a PRS. This is the top level primary reference clock. Now the two terms here on each level, this is our on the left hand side we have the ITU standard, and we have the ITU term, and then we have the ANSI standard and the ANSI term. So the primary reference clock I still always call the primary reference clock, but I call it normally a bits, but in ITU land it's an SSU. And then in ITU land you have your SEC, which is like your normal router would be an SEC. But it's worth noting there's an absolutely equivalent hierarchy for SYNC networks. So when I talked about an EEC, an EEC is down at this level. That's the SYNC version of an SEC or an SMC. In synchronous Ethernet, it's a little bit easier than the TDM, but the hierarchy is exactly the same. One thing I should also point out is that there are actually two ways of distributing time around a network. We've covered really where you have a primary reference clock and you're distributing it through a network. But if you have very good primary reference clocks, then you can sort of have a distributed primary reference clocks. They don't really have to be connected together. Because remember, the whole idea of a primary reference clock is to give us a frequency source. And if the frequency source is 10.000000 megahertz, and the other one is 10.0000 megahertz to like 8 or 10 digits, then it doesn't really matter. I'll put some numbers around this in a minute, but just to give you conceptually. So if the primary reference clocks are all running at the same frequency, it doesn't really matter if they're connected or not. Where it becomes more of an issue is obviously where you've got devices that aren't that quality, then you need to make sure that they have a traceable reference back to a primary reference clock, because a signaling supply unit will not give you 10 megahertz to a lot of digits. It'll give you a lot less digits, and your normal EEC SEC will give you a lot less again. So with G8261, they do talk about the fact that you can have distributed primary reference clocks like that, or you do link them all together. So we haven't talked about the left-hand side, but that's sort of a possibility as well. This probably just explaining a little bit about Sync E again. I sort of mentioned a couple of slides ago about that. Here there's a thing defined called how an Ethernet switch can actually become a source of synchronization. So in a Ethernet based switch, there's things defined in the standards, these interworking functions, which are sort of like magic happens here. But normally you'd have some sort of TDM interface on an Ethernet switch, which allows you to do interoperability then with synchronous Ethernet and with packet-based networks. So we have this capability based on most of our Ethernet-based switches. And what that allows you to do is to take some sort of frequency reference that's not Ethernet, so something like bits or TDM or so forth. There's some magic interworking function happens, and then you have a packet switch network, and then at the other end the opposite can happen, where you have the traceable signal then goes to some interworking function, and then you can have a TDM output as the other end. So this sort of explains, going back to the original, where we're carrying TDM networks over packet-based networks, is you can take the TDM in, you can recover the clock from it, you do this interworking function, you can send the timing information, you send the TDM information, and then at the other end you can actually recreate the TDM circuits by applying the clocking to the TDM circuit and then reconstructing the TDM out of the packet information from the from a pseudo wire type technology. So just to put a line in there about synchronous Ethernet, I'll come back a bit to this issue we talked about with how synchronous Ethernet works. So it's all standards based, and really it's about transferring frequency over Ethernet physical layer. So it's a physical thing, there's no packets involved, right? That's the ESMC side, yes, that's packets. But it's a physical layer, so it actually uses the signal on the Ethernet cable. Now originally, standard Ethernet, as I said, was sort of unsynchronized. Every box talked to every other box. They just set up their own point to point, and whichever one negotiated to be the master, which was based on things like MAC address. Then what they would do is they would use the master's frequency as the signal frequency for that link, and that was pretty low quality. It had a quite a high, the frequency could vary quite a bit. So standard Ethernet, I say there's 125 megahertz plus or minus 100 parts per million. So it could vary by quite a bit. And still be within specification for Ethernet. What Sync E did was it tightened that up quite a bit, and it allowed the clocks on a router to then be synchronized all together. So rather than every port on a router basically doing its own thing, they're all synchronized with the internal oscillator. So that's, conceptually we want to think about it. The important thing with Ethernet, it didn't really change Ethernet at all. What it did was it changed the router or the switch, and the switch now can run all its Ethernet ports at the same frequency, and that frequency is 125 megahertz plus or minus 4.6 parts per million. So it tightened up it quite a bit, and it made sure that every link on that router then ran at that same. As I said here, the clocks are locked and traceable to a master clock, and when you've got them connected together, it's 10 parts per trillion. So the long-term accuracy of a Sync E network is quite amazing. It's 4.6 when you're free running, but when you're actually traceable to a master clock, it's 10 parts per trillion, which is very good. And of course, in the Cisco products, they're supported in most of our service provider or telecom type product portfolios. So one of the things about building a frequency distribution network is there's some rules about how much and how many you can put in a chain, and this is basically the chart. Now, this comes from Sonnet and SDH, but this one's from SyncE, but I mean it's basically a copy from Sonnet and SDH ones. And the rules basically say that you can have a primary reference clock, and that primary reference clock can pass its signal through up to 20 ordinary routers, EECs, and then you need to pass it through one of these SSU devices which has a better oscillator and which is able to clean up the signal, clean up the jitter, and try and reduce any wander that it can reduce. So and then you can pass it through another 20. So what this means is you can have these 20 EECs, and you can have up to 10 of them hanging off it, and then at any one point you can only cross 60 EECs. Now, probably a lot of you have configured routers and Cisco routers and never knew this existed, but even with synchronous Ethernet. But there is actually a set of rules like this. But most people, they just plug synchronous Ethernet together, and it's so good really that it just works. So talking about clocking specifications, I said I'd put some numbers on some of these, so the quality of the oscillators. So this is to give you an idea of just the different levels of quality. So the numbers aren't that important, but just to give you an idea of the scale. Again, we have an ANSI term and we have an ITU term. And the ANSI term is this stratum 1 on the left hand side, and the ITU term, PRS. To be honest, I don't see the ITU terms used very often. Everybody talks about stratum 3 or stratum 3E. So I don't see people talking type 3 and type 4 very much. As I say there, stratum 1s of course are very quite expensive, complicated pieces of machinery. They're based on cesium clocks. You have to recharge them with some cesium every couple of years. They require maintenance. They're sophisticated pieces of equipment. Stratum 2 uses rubidium, which is quite a bit cheaper and easier to deal with. They have got technologies nowadays to do stratum 2 without using rubidium, so there's these double oven cooked oscillators and stuff that's available. There is other technologies out there which I'm sure you can find with Google. And so then they define the accuracy. So you get 1 by 10 to the minus 11, which is extremely accurate. And then the holdover stability, when it's actually not got a reference connected to it. And the time to first slip basically says if at that level of accuracy, how long before you get the first slip on a T1 interface, if you had a T1 connected to those two devices. And as you can see, with primary reference, it's 72 days, which is a fair time. But once you start getting down to stratum 3 and stratum 4, then you can start to get noticeable issues on your transmission circuits, within minutes. This is where we were talking earlier about the length of time you need to be in holdover, and holdover becomes important here because if you don't have a very good clock at stratum 4, then you are immediately going to start getting slips on your interfaces very quickly. So most routers these days stratum 3, most of them going to stratum 3E. What's the difference? It's about cost, really. And but a lot of our routers, the bigger routers, are certainly 3E, and even our access routers are increasingly 3E based oscillators on them. There's some various technologies to do that. The oscillators, of course, being physical devices, they like to change speed when they change temperature. They also sometimes change speed when they're new. So the first 30 days they might vary a little bit in speed. These oscillators, and it's the same for all oscillators. It's these are all merchant silicon, and then they'll settle down and they'll work fairly well for a number of years. And as they get older, they might start changing again. So there's a lot of engineering needs to go into these oscillators to make sure that they don't behave differently when they're new, they don't age badly, and also that with temperature variations they don't change frequency either. So the difference in these, especially the lower levels, is more about the engineering and the cost to make sure that these devices keep to the frequency which they maintain. They should be their nominal frequency. And that then just becomes a cost issue. So you'll see things called TCXOs and OCXOs and stuff. They're just different technologies at a different price point to deliver slightly better oscillator performance. And the consequences of that are, as you see, the holdover performance, and how long before you start getting issues in your network if you lose your references. And I just a note to put at the bottom there. We were talking about Sync E. The original Ethernet, was a lot more loose in its requirements than any of these. So it just shows you the difference that there is there, and with synchronous Ethernet, how it improved it. So we talked a bit down the left-hand side here, just giving you a look at the three ways that we do this traceability of quality level. In the left-hand side we have SSM. So I've just show you. There's a byte sitting in the part of the frame, in E1 and in SDH, and there's 4 bits there which are used for SSM. So that's how it's done on TDM type circuits. And down the left hand side here we'll see this is the quality level. So these are the bits that have been defined for SSM. Then talking about when you're talking about synchronous Ethernet, then we're talking about this mechanism here. So we're sending, remember the synchronous Ethernet is a physical thing on the the frequency on the wire, but it does actually send these ESMC packets over saying what the quality levels are. And the way they do this is it's done with the ESMC options. So it's sending these circuits, these packets backwards and forwards, saying what the quality of it is. And with PTP they're using the one at the bottom, which is this is a protocol which we'll cover in the next section, and that shows really it puts an attribute in what's called the announce packet, and the announce packet has a PTP clock class, and the PTP clock class is defined down the right hand side. Now there are some different versions of that, but in general this is the basic 1588 version 2. So what you can see there also is a basic ability to translate between these various versions. So if you're getting an SSM quality level of 001, that means that you're in an ANSI network and you're getting PRS. You're in an ANSI network and you're getting PRS. If you get a 010, it's an ITU network and you're getting PRC. So if you're connected to option 2 here is ANSI, option 1 is ITU. So what this means is if you get a quality level of 1, an SSM value of 1, it means you're in an ANSI network and you're connected to a primary reference source. If you're getting 10, it means you're in an ITU network and you're connected to a primary reference source. Sorry about that. And then you can see with the various quality levels, you go down to SSUA, SSUB, SEC, which is the normal router, and then the do not use, which means it's not to be trusted. So for option 1, option 2, and then for ESMC, the ordinary option 1, which is the ITU world, has an EEC1 and they have an EEC2. but the PTP clock class then translate to each one of those levels. Anyway, it's not that important, but just so you can see that there is a translation between them. And in fact, when you have a PTP and it's connected to a primary reference clock here, let's say it's connected to an ITU bits interface, then it will transmit in its announce message on 84 saying that it's connected to a primary reference clock, so that then the slave can tell that it's connected to a primary reference. So that's sort of the chart that describes how all these things interoperate. So that's really what I want to cover on frequency. What we cover now is like how we measure it. And we won't spend a lot of time on it, but just to give you some familiarity of what we're talking about with measuring it, because many times you'll hear the customers will want to measure the quality of the frequency recovery, or people will ask you for information about frequency recovery. So we'll just go through some terms as for which we'll use to define this. Okay, so some of the terms that we need to talk about. Probably the most important two are jitter and wander. We've already seen a little bit how jitter works. Jitter is almost a short-term random variation. So when we saw it in a packet-based network and packet delay variation was holding up or various packets, that introduced jitter into our network, into our frequency recovery. Similarly, when we have circuits that are on a physical wire, and get jitter caused by reflections and crosstalk and stuff. Wander is more of a long-term thing, so you'll hear them mentioned together, like measuring jitter and wander. But jitter is a short-term variance, and wander is where things change over time. So you might find that with a clock heats up, you might see things based on a daily cycle where if a clock is in the sun or something and it gets too hot and it starts to go a bit faster or something. There's those sort of effects that are called wander, where you get longer term effects, whereas jitter is more short term. Accuracy is probably the most important. I mean, there's a formal definition there, but accuracy basically just says how close is the result of what we're measuring to what the value of the reference is. So that's very important. And then reliability, it just says the amount of time that you can keep within a specified accuracy. So if you can be accurate to within this particular difference for a long period of time, you're more reliable than one that cannot. So one of the most common methods that we use to measure this is to connect a reference source and to connect our source that we're measuring together into a piece of equipment. I have another slide in a sec. And you measure a few pieces of information. And the most common three you'll see is the tie, the M-tie, and the TDEV. Tie is measured instantly. So what it does is it measures the accuracy, which you remember is the difference between the reference and the measured signal, at a certain moment. So as we're observing the signal, we'll notice the tie will change. You can see here on the right hand side, you can see how the signal, the time is wandering during the observed interval. So you'll measure the tie during this observation time or measurement time, and you'll keep track of them all for statistical analysis. And then at the end of the time, you'll calculate what the maximum tie is, the M-tie, and that basically tells you what was the largest peak-to-peak tie. So during the time that you were doing the observation, what was the maximum that you got away from the maximum variance from the observed signal? And what that does is that indicates not just the accuracy, which is a short-term thing, but it indicates the stability, so how accurate you were over a longer period of time. The TDEV, then there's a bit of statistics that's done, which which indicates the time deviation over time, and say it's a statistical variation, and it tends to indicate more systemic effects on your device. So how does this look in reality? Here we show generally how it's done. I've got a picture of an ANT20, which was a device that was used to frequently do that. There's still a lot around. They're a device I think was bought by Juniper. They're end of sale antiques now, but there is equivalent machinery to do this. I think Calnex and other people make similar devices, so they are out there. And the way that basically works is you take a primary reference clock and you plug one side of it into a router, which is part of your distribution network, and you plug the other side of it into the equipment. So there's your reference signal. So this device is going to have then being able to compare against this reference signal. And then you have your network. You either have synchronous Ethernet, you have TDM, or you have packet-based network. You can do the same thing. And then at the end you've got clock recovery. The clock is recovered, and it is you connect it then via a TDM circuit or a Ethernet, synchronous Ethernet circuit or something into the ANT or the measuring device. And then the ANT then takes periodic measurements as to how far the reference signal is, or how far the measured signal is from the reference signal. And so you can see here on the left hand side, this is the instantaneous. Down the left hand side is the number of nanoseconds that it's wandering away from the source signal. Again, we're just talking about frequency here, so this is it's not actually talking time of day. This is like how far the frequency is wandering from where it should be, and you can see that it varies as time goes on. And then when you finish this, you click a couple of buttons and it calculates the graph on the right, and I think I have it blown up in the next slide. Indeed I do. So the way then it calculates is the MTI and the TDEV, and you'll see here this red line here is the MTI, and the green line on the bottom there is the TDEV, and it calculates those over the period of time that you've run the observation. So in this case it's been running for 10,000 seconds. Normally you run it for a day, which is up to about here. But this has been run for actually it's up the top, 8,000 seconds, 7,200 seconds, and it's calculated the MTI and the TDEV. What you then do is you load a mask in, depending on what is the quality of the device that you're under test. And this is an SEC device network interface, and it's defined in these standards. And what that will do is it will load these masks. So that's the top red line and the top green line. The top red line is for MTI and the top green line is for TDEV. And what this does then is this shows that they're the maximum limits which you are not allowed to exceed. So as long as the red line in the calculated MTI here is below the mask here, you pass. So this is actually passed. Same with the TDEV. The TDEV is here, calculated TDEV. This is the mask for TDEV for an SEC, and so it has passed that as well. As I say, typically run these for a day, and then that'll tell you that whether you'll pass the quality of the for a SEC based network interface. There are masks for all these clock levels, so there's quite a number of them. The other thing we should touch on is, GPS is also a very common source of time, especially where you have remote centers where it's very difficult to get synchronization information to them. Now, when I say GPS here, I actually GPS is the US version of what is a generic family of global navigation satellite systems, or GNSSs. There's a number of them. GPS is the most common, but there's a Russian GLONASS system, and there's the Europeans are building Galileo, and the Indians and Chinese are also building systems. So there's quite a few out there. And so people say, well, why can't we use GPS? And there is some good reasons for using GPS. It's available, just about all over the planet, better in some parts than others, but basically it's planet wide. And it does provide all the three synchronization types. It has frequency, it has time of day, and it has phase. And it's very accurate. All these GPS satellites have various forms of atomic clocks in them. So they're, and a lot of the way GPS works is based on time. So they were designed from day one to be able to support accurate time. I said they're within 100 nanoseconds, but I think nowadays they're down to, I think you can get solutions down to 30 nanoseconds or so forth. So yeah, so there's some very good reasons. The other thing, of course, that it's it's a very well maintained system. It has the US government is underwritten it for many years now, and what they doing, they're improving the system all the time. They're launching new generations of satellites. They're updating the power. They're increasing the power on the satellites. They're putting a refurbished bank of satellites up there. Well, refurbished meaning like a new generation. They are also opening up new frequencies to get around some atmospheric issues. So it's certainly got a lot of momentum behind it. But one of the problems with it, of course, that it's run by the US government, and so not a problem maybe in the US, but outside the US there are some people who are a little bit uncomfortable, let's say. The fact that it's basically a military design system and under the control of the US government. So to be fair, there has been a lot of statements from the US government, basically, saying that they'll never deny GPS capabilities. So you can probably, getting away from the politics of it all, you can go and Google that yourself. But there's certainly some statements around that say that GPS should not be used as a unique reference in any critical civilian system, and the US government doesn't like use it for aircraft or anything like that without backup systems. So it's important to just understand the vulnerabilities there, and just make your own decision. What is clear though is that one of the problems with GPS is an extremely weak signal. I said less than 50 watts depending how you measure it. And the birds are at least 20, 21 or even further, 1,000 kilometers away, which comes down to a figure of, like less than like about a fifth of a femtowatt, which is an exceedingly small signal, which means that it's incredibly easy to jam it. Spoofing is a little more difficult, although I believe they can do a bit of that now. The US military, of course, have encrypted channels on it, and so they can avoid most of the issues with spoofing. They can work around that. But the issues of jamming are certainly a fairly big and almost a daily occurrence, in parts of the world where people are, fairly cheap and portable jammers that can just wipe out the signal for a fairly wide area. So that's an issue. The issue is the cost of installation, mainly siting the antenna. A very weak signal means that you need very good antennas, you need very high gain antennas, you need a very nice location where you can see the sky and lots of satellites. You need a very good cable to be run from the antenna. And then there's all the issues of distributing the signal, whether you've got splitters, every time you've got splitters you need amplifiers, and the length of cable run. So there's a lot of issues about, and cost associated with putting GPS receivers in. I say there are other opportunities to use other GNSS systems. GLONASS was popular for quite a while. The Soviet Union fell apart. GLONASS constellation fell into disrepair. Russian Federation has done a lot to fix that, I believe, nowadays. So GLONASS is, I think, fairly operational. Galileo's, the European Union are launching Galileo, although just last week they launched 2 satellites into the wrong orbit, which wasn't good. So yeah, so there's a lot of options there going forward where people are building receivers. Already Galileo and GPS can work together. They've designed it how it's interoperable with both of them. So you'll be able to get receivers. You can already get GLONASS GPS receivers that can do both systems. So there is some opportunities there to to have some redundancy and so forth. So I just thought I'd put that out there for because I know in the US, for instance, a lot of cell sites and stuff, a lot of it's done using GPS, but other parts of the world, some people have some reservations, and even without that, there are some issues around jamming and so forth, which require mitigation. What some people are doing are deploying GPS as their primary source and then using some sort of network-based distribution as a backup source. We have customers that are doing that. Okay, so that's basically frequency that I covered. What I wanted to do now was just to go through a few slides on phase and time synchronization. It won't be quite as long, and just the idea to explain the differences and the similarities. But I think now we've got most of the concepts out, done with frequency. So now it should be a bit simpler to go through and look at phase and time. Now we showed this slide before. There are some applications where we need phase. Here I'm talking about particular radio technologies, LTE and LTE Advanced and TDD. But there are quite a few other ones that require phase synchronization as well. But whatever the application you're interested in, you'd really have to just understand what your frequency synchronization and your phase synchronization requirements are, and then design the network to support it. So phase and time of day sort of go together. I show here on the right hand side the switch module from ASR 903, which is one of our routers, and you can see here we have the 2 ports on the left hand side. There's 1 PPS, and 1 PPS stands for 1 pulse per second. So I like to say it's an analog signal. It's either goes in or comes out on that port, and I like to think it's it's very much like the talking clock. The pulse per second is like it gives you a beep every second, and you can see on the oscilloscope on the left hand side here that there's a big pulse at this time interval here, where the pulse per second has gone in on the oscilloscope. At the same time, there's a time of day port, which is a serial interface, and it then puts out a text string, like I've shown up up the top here, and the text string actually indicates the time of that the router sees. So a good way to think of this is almost working together like a talking clock. Is that the talking clock would always, when you used to call up the talking clock, it would say, at the 3rd stroke it will be 13, 38 and 54 seconds or something, and it would go beep, beep, beep. And it's a little bit the same, is that you have 1 pulse per second, and then you have a time that's coming at defined as well, that you can use to then put the time of day. So the pulse can be used for phase, and then the time of day using the pulse in the ASCII string. Many formats available. This really isn't important to know, but just so you know, there is actually different formats of time of day. NTP, of course, has various formats, fairly popular. Most of these routers can put out or accept, and most of these clocking devices can accept or transmit time of day messages in various formats. Some of the popular ones are the NTP ones. Cisco has its own format. There's ISO standards of one. There's NEMA, which is the Maritime Engineers Association. So this was for seafarers and so forth who are navigating using GPS and the original LORAN systems and so forth. Loran, gave them time, and there's messages defined by NEMA for all sorts of things to do with equipment working together in a seafaring type environment. But just the point to take away from this is that there is quite a number of different formats which will be you'll need to understand. If you need to plug things together, you'll have to configure them, or maybe do some form of interoperability to determine what's compatible with what. Okay, so we know that there really isn't, for all intents and purposes, there isn't really a physical distribution mechanism for time of day and 1 pulse per second. Practically, the way this is done is using packet-based mechanism, and the most common is to use PTP IEEE 1588. And what we do is we have a master, and like before, we'd have a master that had a frequency reference. What we can also do is have a time source for time of day and 1 pulse per second. So just going back to the slide before, if this ASR 903 here on the right hand side was a 1588 master, then you would connect like a GPS with 1 pulse per second in, and you'd connect the 1 time of day here, and that would give you the time reference, the phase, and the time of day reference. You could also use the GPS to connect to 10 megahertz in here to give you the frequency reference. So going back to the master, we have a frequency, but here we're talking about time of day, so we connect the 1 pulse per second, and the time of day input we configure whatever format it requires, and then it does the same thing by generating packets, sending it out across the network, and then we have slaves at the network who recover the frequency, who recover the time of day and the 1 pulse per second. So here you can see at the bottom we've recovered the time of day and the 1 pulse per second. Now if we take our reference source, I've shown the pulse up here in blue, and this is our reference signal, and you see the pulse here, and the blue boxes sort of represent the time of day messages conceptually. Here at the other end we have recovered the time of day and the 1 pulse per second, and you see there's a little bit of a phase offset here. So you can see the blue line, the phase starts here, and the recovered is a little bit. So there's a bit of a phase offset, which is an error which you would get in the network. So when we're talking about how many microseconds that we want for our phase budget, this is what you're talking about. If it's 1.5 microseconds, then you have to keep that phase offset under 1.5 microseconds. So here you can see the time of day messages have arrived, the 1 pulse per second, they say slightly out of phase but not too bad, and then the time of day messages have been recovered as well. So you can similarly to before, you can take the 1 pulse per second reference signal here, and you take the 1 pulse per second recovered signal here, and you can compare the quality of those. So in this case, if we have like a cell site that requires phase, then we can recover the time of day and the phase out here at the slave on the cell site, and then using the 1 pulse per second out plug, we can actually give 1 pulse per second to the cell site equipment if it requires it. So you put your time of day and 1 pulse per second in here, and at the other end you plug it into the cell site out of the output plugs, and that way you've carried phase and time of day across the network. As you see, there's a slight error there just because of electronics and packets and so forth, and that's really you have to test and understand for your application whether that's going to be good enough for what you require. I think I should just point out NTP is probably the most widely used time of day distribution mechanism. Up to NTP, most commonly used NTP v2 or v3 is what's used to distribute time of day amongst your routers and PCs and your iPhones and so forth. I will normally NTP doesn't actually give you the sort of accuracy that you're looking for. Within it, you're talking certainly a lot of deployed NTPs. Be lucky if you can get 50 milliseconds of accuracy, whereas the PTP has been designed to give down sub-microsecond accuracy. So there's orders and orders of magnitude difference in the accuracy of this, and there's reasons why that is. Mainly because of the use of hardware assist for things like timestamping and so forth. So just covering phase accuracy, we sort of saw it on the previous slide, but I sort of blow it up here to just explain, like when you get a slight different distance in the pulses, there's a bit of an offset or a pulse spreads out or whatever. You take a reference signal A and a recovered signal, and you compare them, and you'll find out that there might be a slight difference in phase. So when we talked about the phase requirement, whether you require 1.5 plus or minus microseconds, then that's really what you're measuring. You're measuring how close you are to your reference signal. And if you have base stations that need to be synchronized to 1.5 microseconds, then in this case we're getting plus or minus 1 microsecond of error. So it's plus 5 and minus 1. So you generally say that's plus or minus 1 microsecond. So you're within your phase requirement. So it's just depending on the application you need. So what have we learnt? We've seen that there's plenty of applications in industries which need synchronization. We give some examples. We sort of focus a little bit on mobile, but yes, I'm sure there is certainly plenty of other applications, whether industrial or electrical and so forth, that need sync. We've seen already that the standards organizations are all over this. It has synchronization has come from the TDM world. It's been around for a long time. What's new really is bringing phase into it, and also bringing it into the packet-based world, and tying it in with Sync E and tying it in with packet-based distribution. That's sort of what's new. There's 3 basic parameters for synchronization. There's frequency, which is pretty much required everywhere. Phase, which might be required based on certain certain criteria or radio technologies or so forth. And then you've got time of day. We have distribution of frequency, can be either physical based or packet based, but phase is packet based. For physical distribution, we can normally we use Sync E or TDM circuits, so like Sonnet or even E1T1. You can have in band or out of band, where like you have a bits interface on every router. But normally it's in band, where you carry the clocking signal with the data circuit. We've got mechanisms to track the traceability of a clock, and also to indicate the quality of the clock, and then to make the decisions on which clock to select based on things like the clock quality and traceability. And phase and time of day is commonly distributed with 1588. And we've seen that with 1588 we have to be very careful about quality of service, using priority queues, hardware switching. We have to be careful to minimize PDV and to also avoid asymmetry. And for that we'll talk more on in part 2 of the synchronization and timing bootcamp. Thanks for listening.